Okay, hello. Um, I'm going to try to explain entanglement uh, in layers. This is an onion in layers of an onion. We're going to start with layer zero. Okay, so here's layer zero. Um, we have a pair of particles, and they start out very near each other, and then they are entangled, and then they are separated a very far distance apart, a light year apart. After they are separated, they are measured, and out of the measurement will pop a 0 or a 1. And let's say that this one is a 0, then miraculously this one will be a 1. um, this this is a, so then along with this explanation is also that the particles weren't anything like while they were traveling. It wasn't a 1, it was a superposition of being a 1 and a 0, and this one was also a superposition of being a 1 and a 0. So they say. And the only issue with this is that it really seems like this was just a 0 all along, and this was just a 1 all along. And although the scientists say that it wasn't, like, it's pretty hard, it's not very convincing from this setup. Anyway, so that's layer 1. That's layer 0. Here's layer 1 of the onion. A slightly truer and a slightly falser explanation. So we have our two particles. We entangle them, and then they're separated. And remember, this is not correct. This is wrong, what I'm going to say, but this is just in some sense less wrong than the previous layer. Whichever one is measured first will be, let's say, a 0, and whichever one is measured second will be a 1. Then that is more to the spirit of how miraculous it is what entanglement does, because over a long space, how could it know which one was measured first? How could it communicate that to the other one in time for it to know what to do? That's interesting. It's a red dot. That's cool. Anyway, the only problem with that is that it lets you do something that entanglement doesn't let you do in reality. This would let you communicate back and forth if you had a bunch of these entangled things. Because you could, when you measured your thing, you would know whether they had measured theirs, and you could keep some clocks and usefully use that information. But we'll see that entanglement doesn't let you usefully use the information. So let's go to the next layer. There are just 4 layers. Well, I mean, we started at 0, so I guess there are 5 layers. Anyway, in this layer, we're going to imagine that our particle is um, we have our two particles. They're entangled, and when they're separated, we have um, an option about how to measure them. We'll say that one of our options is to measure it up and down. But our other option is to measure it side to side. And we can measure either of them either way. It's a choice. Either way that we measure it will result in a 0 or a 1. But if both people measure it the same way, like if they both measure it vertically, then it'll turn out, because they're entangled, that they're both the same. Maybe they're both a 1, maybe they're both a 0. We'll say that they both outputted a 1. If they are both measured horizontally, then they should also output the same thing. We'll say in this case that they output a 0. If we did that, it's possible that one person measures it side to side and the other person measures it up and down. In that case, they should be opposite of each other. Remember, this is a lie. We're only at level 2 or level 3, whatever, in the onion. So let's say that this one outputs a 0 again. And this one outputs a 1 again. We can see that this is, it kind of has the same issue, you might say, of the layer 0 of this onion, which is that we can sort of just, it's not so miraculous that they're the same number. Like we could just make it so that if you measure it vertically, it outputs a 1, and if you measure it horizontally, it outputs a 0. And then it'll sort of do everything you need. If both people measure it vertically, then they'll both see a 1, and it'll be the same as each other, so that's great. And if they both measure it horizontally, then they'll both see a 0, and if one of them measures it horizontally, they'll see the 0, and the other person, if they measure it vertically, will see a 1, and that works out as well. So it's, and we could have just reversed all the 0s and the 1s, and it would still be, these people would still see the same thing. They would see a 1 in that case. In any case, so it's still not super miraculous, it seems. It seems like that could happen even without quantum mechanics. Anyway, so let's go to the next layer. We'll call layer 3. So we have our two particles, and they're entangled. And then we decide that there are 3 ways to measure this thing. And both people have all 3 choices. And we'll say that what we want is, if both people measure it the same way, whichever way that is, they should get the same result. if one person measures it one way and the other person measures it diagonally, they should get the same result. They should always get the same result unless one person measures it up and down and the other person measures it side to side, in which case they should get a different result. This, it turns out, is, I claim, impossible to get this to work out with an ordinary non-quantum mechanical classical environment. Basically, if we decide what we're going to do when this person measures it in the vertical way, we'll have to do something. Let's say that we show a 1. Well, this person it'll need to be the case that when it's measured vertically, they'll need to see a 1 as well in order for these to be the same. But that also means that if this person sees the side to side or the diagonal measurement, that needs to also be a 1, because it might be that this person measures it up and down and sees their 1, and we need to be the same as them in that case. So this needs to output a 1. But that also means, for this same reason, if this person measures it horizontally, and this person measures it diagonally, these need to be the same as well. Which means that this person's horizontal measurement also needs to return a 1 in case they both measure it horizontally. But that's not good, because if this person measures it horizontally and this person measures it vertically, they need to be different in that case. And so there's no way to work it out. The only thing that's problematic about this layer of the onion is that that is not possible. It's not possible to do this with entangled particles. But you can do something close to this, and we'll see that in the next layer. Okay, and this is the final layer. What you can do in real quantum mechanics, as far as I understand it, if you have two entangled particles, there are really, in some sense, 3 ways that it can be measured. As far as I know, these ways are, in fact, can amount to how much you twist a measuring device that you're going to put this thing. I don't know exactly how. I haven't run the experiment. It'd be interesting to see. In any case, my understanding is that you can, and mathematically, I understand a bit better the sense in which you can measure this thing in these 3 different ways, and that there's it's not entirely a fiction that it's drawn on a circle like this. I believe it's the case that the crucial bit here that a diagonal measurement is correlated with a vertical measurement, and it's also correlated with a horizontal measurement. It's not correlated 100% like in our previous onion layer, but it is correlated in amount that's sort of related to where this line is on this diagram, which importantly is above, or in this case beyond, a point of 75% of the distance from here to here. That is to say that if one person measures vertically and the other person measures diagonally, the probability that they get the same result is more than 75% with a real quantum particle. And the probability, if one person measures it vertically and the other person measures it horizontally, is 50%, rather than 0%, or 0% from the previous layer. That is to say, there's a 50% chance that they'll be the same value and a 50% chance that they'll be different. Whereas in this case, if one person measures it vertically and the other person measures it diagonally, or if this person measures it horizontally and this person measures it diagonally, the probability that the result will be the same is more than 75%. It's some value roughly here, from here, I think. But what's important is that it's more than 75%. That I'm very sure is true, and is the reason that you run into the same sort of logic issue from before, which is that if we want to arrange things with our two particles so that they give the right results under the right conditions, we can kind of imagine on one side that we have what we need to do if this person measures it vertically. And let's say that we have 100 particles and we're going to have all of their results be a 1 if that person measures it vertically. Over here, if this person measures it vertically, these all need to be a 1 because it needs to be the same as the other person if they measure it the same way. Now, if this person measures it horizontally, then because this person might measure it vertically, and if they do, they'll get all these 1s, and if this person measures it horizontally for every time, there needs to be a 50% correlation between the two. And so there needs to be half 1s and half 0s. If this person measures it diagonally, because this person might measure vertically for everything and they have all 1s, if this person measures diagonally in that case, this needs to be more than 75% correlated with all 1s. So we have 50% ones. And then over on this side, we have more than half ones, and then we have zeros. That's a problem because if this person measures it horizontally, then all of their values need to be the same as all of these. But if this person measures it horizontally and they get these values, and this person measures it diagonally, then these two things need to be more than 75% correlated. And we can get a good amount of correlation from the ones. We get 50%, but then now we need to be correlated with these zeros. But the thing, we're already more than half ones, and so we can only, at best we can be correlated with this less than half of the, less than a quarter zeros here, which doesn't give us our more than 75% correlation that we need. And so it's and so there's no hidden variables solution. There's no way to arrange it classically where the outcomes could be the desired way. Yeah.